Assalamu alaikum. I welcome you all to another lecture on electrical machines. In the last class, we discussed about a transformer equivalent circuit and we studied two very important tests of our transformers in which we calculated the values of the equivalent resistance offered by the primary winding as well as on the secondary winding. We also studied in that particular lecture that how to find the components of the excitation branch of a transformer, and for that we undergone two different tests. One was the open circuit test and the other one was a short circuit test. In the today's class, we will discuss three different topics. One is the expression of our system, power system, in terms of the per unit values. Thereafter, we will see the transformer regulation concept and the efficiency of a given transformer. So let us start with the today's class. The per unit system of measurement is actually a unified form of a power system where everything is converted from their original value to a per unit value, so that all the values comes in close proximity to each other. For this particular system, which is actually a dimensionless system, we take the per unit value as equal to the actual value of the power system divided by this base value. Now, what is this value? This value could be a voltage, it could be a current, it could be the impedance Z, and it could be the power. Whereas this base value is that particular value of a power system which is considered the standard value. So everything is converted into a base value first, and thereafter we calculate the per unit value. It has a lot of advantages in the advanced courses on electrical power system, particularly in the power system analysis course, the power transmission course, and in power operation and control. What is the advantage of using a per unit system? The first advantage is, number one, it is easier to solve circuits with lots of transformers and generators. And because the transformer and generator may have different parameters, so in order to standardize them, we convert them into a per unit value, and thereafter the circuit becomes very simple to solve. The second advantage is the mathematical conversions they are handled automatically by this particular system. So, in a given system, we do not need to transform the impedance from the secondary side to the primary side or from the primary side to the secondary side. For example, if we have a system, let us say this is our generator. Here we have a transformer, and this transformer is a unit transformer, so it is connected with some transmission line, which is then connected to another transformer which is feeding some load, and that load has some impedance, this ZL, and this is the ZTL. Now, if we want to find out what is the total power supplied by this generator to this particular system, or if we want to find out what are the total losses here in this transmission line, the procedure is a little bit complex. So what we do, we transform this ZL onto this particular side. That is, we refer this, for this transformer T2, we refer this load resistance or the load impedance onto the primary side by multiplying it by this A square. Once this ZL is somewhere here, we eliminate this T2 and then we combine this Z total by adding the transmission line resistance and this reflected impedance on the primary side, A square ZL, that becomes equal to that total. And then this is again converted here by multiplying it with this A square. And thereafter, once we have this particular, every impedance on the primary side referred to the primary side of this T1, thereafter we can have this IG, and then we can, on the next step we convert this, or we send this, reflect this impedance back to their original values to find out what is the transmission line current, and hence what are the losses that are encoded in a power system. Notice here that we have only two transformers connected here. We have this T1 and then we have this T2. We can have a large number of transformers connected in a given power system, and therefore we require to have a systematic approach where we can actually eliminate the transformers from the system such that a simple circuit is formed which is easier and convenient to solve. So let us move ahead to solve such type of a system through the per unit system. So for that, the first thing is that we need to convert there are two steps in this thing. The first step is to find the base value, and the second step is to use the base value to find the per unit value of either the current or the impedance or the voltage. So in a given power system, the first question is that what are the choices in selecting the base value for a given per unit system. So usually there are some practices which are adopted by the practicing engineers. One is that if we have a generator in the system, its voltage and the apparent power are selected as the base value, right? So for example, we have in this particular circuit this Vg, and whatever is the power rating of this particular generator, that will be selected as a base value. If we have multiple generators connected in a given system, then for multiple generators, the generator with highest rating is selected for as a base value. If we do not have the generators connected in a system, we have some system that is only a representation of a transmission line. There we can have any point selected as a base value. So it's actually a choice is left on the designer, or it's an arbitrary choice about the selection of the base value, and usually that is left on the designer's perspective, whosoever is actually designing that particular system. So in here we have, as we have said, that we require to have two values of base quantity. One is usually the voltage, and the other one is the apparent power. So now that we have this V base and this S base available, we can actually find out the rest of the things. How? By actually applying the simple circuit analysis laws. That is, we do know that this S base is equal to V base into I base, and hence we can actually find out what is the current flowing for a particular base value. And similarly, I can find out this Z base by first getting this I. This Z base is equal to V base over, this is V base over over I base, right. So this is the per unit system. We require to have two values and then we convert it into this particular per unit quantity. But the base value selection is very important. The next important point here in this particular system is that for a transformer, when we have a transformer, we do assume that this power which is input to the transformer is equal to the power output, and therefore this is true for this Q in as well as this S in, which is the apparent power. So this remains the same. However, for all these criterias, this V secondary and this V primary may not be equal, right? They may not be equal, because if it is a step up transformer, then the secondary voltage is greater than the primary voltage, and if it is a step down transformer, then we have the primary voltage more than the secondary voltage, which means that while we undergo with this per unit system, we have this power will remain the same for anything which is connected on this primary side as well as on the secondary side. So for example, we have this V base here, and we have this S base available here. So this S base for this side of the transformer will essentially remain same for the secondary side of a transformer. But this V base has to be transformed based on the turn ratio, which is NP ratio NS. So we have to, so this V base 1 may be different than this V base 2, and hence the impedance of the secondary side or of the other side of a transformer is not the same compared to the impedance on the primary side. So these are the two things that are important. So let us solve one example before we proceed further. So suppose that we have a transmission line that has a transformer connected with the generator. After this, we have a transmission line which is then again terminated on a transformer, and after the transformer we have a load which is 10 minus J 30, right. So this transformer, let us say it has a turn ratio 1:10, and here we have a turn ratio 20:1. So here we have the I load, this is the V load, here we have the generator which is Vg, and that is equal to 480 at an angle of 0 degree. This is 20 and this is J60, and this whole is actually the impedance of the transmission line, right. So let us divide them into three regions. This is region number 1. This is the transmission line region, which is region number 2. This is the load section, which is region number 3. For this particular numerical, let us say that the base value is this Vg, that is equal to 480 at an angle of 0 degree, and the power, apparent power S base, this is V base, and this S base is equal to, it is 10 kVA, right. So to solve with this particular numerical, we have to first of all find out the base values for region number 1, region number 2 and region number 3. So for that, let me draw a chart here. This is the base value for region number 1. This is base value for region number 2, and this is base value for region number 3. Remember that these transformers are actually creating the regions. So whenever we have a transformer, there is a change in the voltage, and that change in the voltage has to be reflected on the other side of a transformer, and therefore we have segregated them into 3 different regions. So for this region number 1, the base value V base is equal to 480 at an angle of 0 degree, and hence we have this S base equals to this 10 kVA. So what else we can get through these two values? The first thing is we can find out what is this I base 1. So I base 1 is equal to V base over S base, and hence that is equal to 20.83 ampere. This is the I base 1 or the base current for the region number 1. Next thing is we can find out what is this Z base 1, which is the impedance offered by this region number 1. So that is equal to Z base is equal to V base over the I base. So if I divide this by V base divided by the I base, I get which is equal to 23.0404, right? 480 divided by I base. So we normally do not write this here, so that is just 480 volt. So for base value for region number 2. Now that when we shift from this region number 1 to this region number 2, we cannot neglect this turn ratio here. So this turn ratio has to be reflected on the secondary side, so that we can actually eliminate the transformer from the power system. So if I do so, then this V base 2 is to change, and that is that this V base 2 is actually greater than this V base 1 because it is actually a step up transformer. So this V base 2 becomes equal to 4800. But like I have said that for a lossless transformer, the input power is equal to the output power. So is the case with this apparent power. So this S in is equal to S out, and therefore this S base 2 remains essentially same as this 10 kVA. Now because we have this V base and this V base change, therefore the I base 2 is equal to 2.083 ampere, right? So this is the total amount of base current which is flowing in the region number 2, and therefore this Z base 2 becomes equal to 2304, right? So for this region number 3, we need to find out the V base 3. So this V base 3 is now decremented 20 times because we have a transformer here. So if I divide it by 20, I get 240 volts. This is the base value for the region number 3, and therefore and also by applying that this S in stays equal to the S out. If it is a lossless transformer, then this S base 3 is equal to 10 kVA. So this whole line, if you can see here, this remains essentially the same. There is no change in the apparent power of a transformer, and so the S base remains the same. The third thing is to find out this I base 3. So I base 3 is what? It is V base 3 divided by this S base 3. So when I divide this, so this is S base, sorry, we have another mistake here. This is not, this is S base. This is S base and this is the V base. So here we have I base is equal to 10 kVA divided by 240, and therefore this I base 3 turns out to be equal to 41.67 ampere. And so is our Z base, that has now changed to 5.76 ampere, right? So now that we have calculated the base values for all the regions, we have calculated the impedance base value for region 1, region 2 and region 3, and also we have calculated the currents values for and the voltage value for all the regions. So now what we can do, we can now shift this whole diagram into a per unit system. So remember that for a per unit value, we have earlier seen that the per unit value is equal to the actual value divided by the base value, right? So let us convert this particular transmission system into a per unit value. So this is Vg. If I draw this particular system, I can get rid of the transformer now because it is already reflected into the base values. So the transformer is now neglected. We have this type of a system. Here we have this load. Now this part is this region number 1. For this part, this is region number 2, and this region number 3 is this particular part, right? So, what is the value of this Vg now? This Vg in per unit is equal to 480 at an angle of 0 divided by the base value for region number 1, which is 480 volt. So, if I divide it by 440 volt, I get 1 at an angle of 0. Right. Next come is the impedance which is present in the transmission line. It was 20 plus J60. So, in per unit values, this Z is equal to 20 plus J60, that is the original value divided by the base value. And the base value is what? It is 2304 ohm. So, that is equal to 2304 ohm, and that 0.0087 plus J 0.0260 in per unit. So, this resistance has a value of 0.0087, while this inductance has a value of J 0.0260. For this particular load, we have in per unit value, it is equal to the 10 minus J30 divided by the base value of this particular region, which is equal to 5.76 ohm. This is equal to 5.76 ohm. So, divided by 5.76, it gives me a value equals to 1.736 at an angle of 30 degree in this per unit, right. So, now that we have everything in the per unit form, you can see here that the transformers are gone from this particular system, and everything is automatically taken care by this particular system in the per unit values. So, we have reflected everything here. Now, we can do the mathematics to find out what is the voltage drop in this particular transmission line and what is the power which is delivered to the load, right. So, for that, let us find out what is the current. So, I per unit is equal to Vg per unit divided by the Z transmission line, this Z transmission line in per unit plus the Z load in per unit, right. So, that is equal to, this is 1 at an angle of 0 degree divided by 0.0087 plus J 0.0260, and on the other side we have 1.736 at an angle of 30 degree. So, this turned out to be equal to, this I per unit is equal to 0.569 at an angle of minus 30.6 degree in this per unit. So, this is the total amount of current which is flowing here. This is I per unit. Because it's a series circuit, so everything is connected in series. So, I per unit is also the current which is flowing through this region number 2 as well as from the load. And therefore, we have actually applied this Ohm's law for this AC circuit. So, I is equal to V per unit divided by the total impedance offered by this region number 2 as well as from the load. As far as this primary side is concerned, for this T1, which is the region number 1, there is no impedance shown for this particular numerical. So, now that we have calculated this in terms of the per unit value, we can find out what is the P load in per unit is equal to I square per unit into the real value or the R of the load, because this load has it's a complex one, so it is R plus JXL, right. So, we do have the impedance available here, but the real power is always, it is concerned with the resistance only. So, that is the R load. So, if I convert this 1.766 at an angle of 30 degree, if I convert it into this particular form, it becomes equal to 1.503 plus J 0.868. So, here we have 0.569 whole square, and this R, which is the load in this per unit value, it is equal to 1.503. So, that turned out to be equal to 0.487 per unit. So, this is the per unit value of the power which is supplied or which is used by this particular load. So, if we want to find out what is the actual power supplied, then the actual P load is equal to per unit P load multiply by the base value of the power, right. So that is equal to 0.487 into 10,000, because it was equal to 10,000 kVA, and that turned out to be equal to 4,870 watts. So this way we can get, once we have this particular system, we can actually change the values and the parameters of the transformer and the generator, and we can see the effect directly by converting it into a per unit value. So this is the total amount of power which is used by, or which is absorbed by the load. As far as the transmission line losses are concerned, the power which is absorbed in the transmission line in per unit, that is equal to I square of the transmission line into I square into per unit into R of the transmission line in this per unit value. So above we have seen that this 0.0087 is the resistance. So 0.0087 into the current, which turned out to be equal to 0.569 whole square, and therefore the transmission losses in per unit value is equal to 0.00282 per unit. So now what are the actual line losses in a transmission line? That are equal to 0.00282 times the base power, which is equal to 10,000, and that turned out to be equal to 28.2 watt. So this is the total amount of power which is dissipated in a transmission line, and this power per unit system is a very, very handy system and a very important system as far as the power engineering is concerned. Let us have some general comments on this per unit system. So some general comments on this per unit system. The first thing, if only one device is analyzed, then its own ratings are usually used as a base for per unit system. This is the first thing, right? Number two, if we have a transformer and a generator network, normally generator is preferred for the base value of the per unit system, right? Number three, in terms of the equivalent circuit of a transformer, this R equivalent is usually about 0.01 per unit, and this X is varies from 0.01 to 0.02 per unit. Also, the RC, in terms of the per unit value of a given transformer system, this XM is between 10 to 40 per unit, which shows the magnitude high value of this RC, and this XM is about 50 to 200 times the per unit value. Another important point is, a good practice is to select the base quantities that are equal to the largest component in the system, right? So that's all for the per unit system. Let's move ahead and try to see how we can quantify the performance of a given transformer. The transformer quantification or the performance of a transformer can be seen in context of two values which are known as the voltage regulation and the transformer efficiency. So let us first of all see what is a voltage regulation of a transformer. Voltage regulation of a transformer is actually a measure that how much the secondary side voltage of a given transformer varies when we apply full load to the transformer. So for example, I have this given system. Here we have the secondary side open circuited, and therefore we can say that this Vp is equal to Vp over Vs is equal to Np over Ns is equal to A, and therefore this Vs is equal to Vp over A, because there is nothing connected. So there is no current which is flowing into the out of the transformer. So if we draw the equivalent circuit here, then in that particular equivalent circuit we have only the excitation branch playing its role. So there are the losses in this Rp and this Rs, they are zero, approximately zero. We do have some losses in this Rp, but compared to this Rc, they are also approximately equal to zero. So there is no loss in the secondary winding impedance, and therefore this is one criteria, it is at no load. Now if we provide some load here, what happens? If we add some load to the transformer secondary, like here we have connected some load here, then we have a current that flows through the transformer windings, and that in turn create the drop in the primary resistance as well as in the secondary resistance. So therefore the voltage at the secondary will not be the same as what we expect at the no load condition. So this condition, that how much of the voltage on the secondary side is affected when we load a given transformer, is an important criteria to measure, and hence it is known, and thereby it is known as the voltage regulation of a transformer. So the voltage regulation of a given transformer VR is equal to voltage of secondary at no load minus the voltage of secondary at full load divided by the voltage of secondary at full load multiply by 100%, right? So we want to have a transformer where the secondary voltage remains essentially same irrespective of the loading condition, if it is open circuit or if it is fully loaded. If these are the two loading conditions, then we want to have the secondary voltage exactly same as the voltage that we obtain at the no load conditions. But this do not happens in the theory, in the practical, because of this Rs present in the secondary winding. So the voltage at no load on the secondary minus the voltage of the secondary at full load divided by the voltage secondary of full load into multiply 100 gives us the voltage regulation of a transformer. Now we also know that this VSNL is equal to this VSNL is equal to this Vp over A, and therefore we can also say this is Vp over A minus Vs full load divided by the Vs into this full load, right, minus Vs into full load multiply by 100, and this gives us another expression of finding the voltage regulation of a given transformer. Now in terms of the per unit value, this is in terms of the normal expression, if I compare it, or if I rewrite it in terms of the per unit value or the per unit quantity system, that is equal to V primary per unit minus Vs full load per unit divided by Vs full load per unit multiply by 100%. So as you can see here, because we have actually introduced the per unit system in the voltage regulation concept, this A is now removed, because whenever we operate in a per unit quantity, this A is automatically included in the calculation while we undergo with the base values and the per unit values. So therefore this Vp over A, this A is gone, and we are only left with this Vp per unit minus Vs full load per unit divided by Vs full load per unit multiplied by 100. So what is the ideal value of this voltage regulation? This voltage regulation ideally should be equal to 0. So that is, we always have this V secondary at no load should always be equal to V secondary at full load. So this is an ideal value, that the voltage regulation is always equal to 0. as far as the practical is concerned, the less the value of this voltage regulation, the better is actually a transformer design. Now, to find out the concept of this voltage regulation, phasor diagrams are quite important. So let us have some overview of the phasor diagrams for a transmission system, for a transformer. So suppose that we have an approximate model. We have an exact model here in which we have actually applied a little bit of approximation here. So we have, this is the Vs, this is the Is, this is R equivalent, this is Jx equivalent, this is Jxm divided by A square, and this is Rc divided by A square. So this shows that the system is actually referred to the secondary side. So here we have this IPA, this is equal to Vp over A. Now, to understand the voltage regulation concept in context of the power factor, we need to use the phasor diagrams. Now, just for a little revision, phasor diagram says that if we have an applied voltage V here, we have the current here, then for the resistance, if this is the voltage and this is the current, both are in phase because resistance do not offer any phase difference between the current and the voltage. For an inductance here, if we have the voltage applied here and this is the current flowing here, then the voltage and current in ideal 100% inductive circuit, we have a 90-degree difference between the voltage and the current, such that this current lags by the applied voltage by 90 degree. For a capacitor with the same voltage and the current terminology, we have, this is the current and this is the voltage, that is the current leads the applied voltage by 90 degree. Knowingly that we have either the inductance or the capacitance or the resistance in a given load, we can also have that for an R plus L load, we may have a voltage here and the current somewhere here, where this theta defines the power factor of that particular load. So larger the amount of the resistance in a given load, the more we are towards a unity power factor where the current is essentially in the same direction as that of the voltage. And if the share of the inductance in a given load is more than the share of the resistance, then we fall somewhere here tending towards this particular current direction I, where I is ideally at 90 degree with the V in case of an inductance. So for designing the phasor diagram here, let us first of all apply the KVL on the outer loop. So if this is the whole outer loop and I apply the KVL here, then this KVL says that we have let us say that we have something here with this side positive. Also we have this Vs with this side positive. So this is positive and this is positive. So this KVL says that if we have a current flowing here, then that is equal to minus Vp over A plus suppose that we have the current Is. This is Is into R equivalent plus Is into X equivalent plus Vs, and that is equal to 0. Because in any closed path, the sum of the voltage should be equal to 0. So if I rewrite this particular thing, then this Vp over A is equal to Is R equivalent plus Jis X equivalent plus V secondary, and that is equal to. So if I graphically try to demonstrate it using the phasor diagram, then let us say that we have this Vs as the base value. So this is the Vs, and I have a current Is somewhere here. Let us say we have a lagging power factor. So this is the theta and this is the Is. So right parallel to this thing, we have the load which is drop across this resistance. So this is Is into R equivalent, and from here we have to draw a 90-degree line here, which represents the J times Is into X equivalent. And here we have the Vp over A, or the voltage which is on the primary side of a transformer, or which is actually the voltage at no load. So you can see here that the Vp over A represents that we have the voltage more than the secondary voltage Vs. And why we have this Vp over A greater than this value of Vs? because we have drop across the series element, which is this IS equivalent and J IS into X equivalent. If we have a unity power factor, this is for a lagging power factor. For a unity power factor, what we have, for a unity power factor we have, if this is the Vs and then we have this Is, then of course we have to add some drop here, which is this Is into R equivalent, and here we have to add up the JIS into X equivalent, and this is the value of the Vp over, this is the value of Vp over A, right. So this Vp over A and this Vs, if we have a unity power factor, their phasor diagram looks like this one. So this is for a unity power factor. We will do an example here in the next class, so that we can understand how the phasors are very handy in actually determining the the regulation of a given transformer. Suppose that we have a leading power factor. If we have a leading power factor, then if this is the Vs and this is the Is, then this is the Is into R equivalent, and here if we draw the 90 degree here, this represents the J time Is into X equivalent, and this is now this is now the and this is the Vp over A. Now you can see here that if we have a leading power factor, then the system may become untenable. Then the for a leading power factor, if you can see here, this voltage regulation is negative. What does this mean? This means that the voltage at no load is less than the voltage at full load, right? And this condition is not a stable condition. So this whole condition is actually unstable. Why it is unstable? Because there might be many loads that will draw more power when the secondary voltage is more than their rated value, and therefore they will draw more amount of current that will in fact that will increase this particular vector and thereby increase this particular ISR equivalent. And as we have more value of this ISR equivalent, we have lesser primary voltage as well. So this is actually an unstable condition, and it usually happens if there is a problem in the removal of the power factor correction capacitors, right? Power factor correction capacitors, they are usually installed in the system. So if there is a problem in detaching those power factor correction capacitors from the particular system, the transformer voltage regulation may become negative, and by saying this, the system may become unstable. So this is the transformer voltage regulation. Now that we have seen this thing, let us talk about the efficiency of a given transformer. Efficiency in a particular meaning, it says that if we have actually applied some power from the input side, how much of this power is actually received on the secondary side. So efficiency is what? It is equal to the output power divided by the input power multiplied by 100%. So ideally it should be a 100% system, so that we have P output equal to this P input. So this efficiency is equal to 100%. But as we have seen, there are lot of losses in a given transformer, and those losses actually pay their toll while we calculate the efficiency of this of any machine, particularly this particular transformer. So while we have the losses available, we can say that this input power is equal to the output power plus the losses in a given system, right? So the efficiency which is not equal to 100% for a particular transformer, it is because of these losses. And what are these losses? These losses are the copper losses, right, that are obtained by the short circuit test. And then we have the core losses, which accounts for the hysteresis and the eddy current losses, right? So we have two type of losses in a given transformer. One is the core losses, another one is the copper losses. Among them, this copper loss, this copper loss is dependent on the amount of the current that flows through the winding. Whereas this this core loss, which is PC, it is usually fixed. Why it is fixed? Because these core losses are dependent on the peak flux, and this peak flux is dependent on the applied voltage. Because this applied voltage is usually fixed, therefore this PC is a constant loss. It do not depend on the value of the load which is connected on the given transformer. Whereas this copper loss, P copper, it is load dependent. Right? So if we have a full load connected with the transformer, it will produce losses according to that particular current, because these are the I square R losses. So if I may draw again, the equivalent circuit of a transformer, we have, for instance, let us draw this simple model. We have this R equivalent, this is JX equivalent, and this one is the RC that corresponds to the losses in the core. These are fixed losses, as I have said, because they depend on the flux value, which is dependent on the input voltage, and usually the input voltage is essentially constant. Therefore, these losses are fixed, or we can say these are the constant losses in a system. Whereas this R equivalent, what are the losses here? It depends on this I. So we have I square, if this is IS and this is R equivalent, right? So it depends on the value of the amount of the current which flows through a transformer when it is connected with the load. So we have variable losses as well as the fixed losses. So this P input, which is equal to the P output plus P loss, I can actually rewrite this as efficiency is equal to P out divided by P input plus P loss into 100%. Now further, if I move ahead, I can say that this P out is equal to VSIS cosine of theta, which means that the output power is not only dependent on the secondary voltage and the secondary current, but it is also dependent on the load power factor, right? And this IS is also dependent on the load. So the load power factor as well as the percentage loading is an important criteria in understanding how the efficiency of a transformer is actually varied. So let us say that this efficiency is equal to VSIS cosine theta divided by the power on the input side. Now because this is not the power out, this is power out, right? So I have written it wrong. Let me correct this one. This is P out plus the P loss. So that is equal to VSIS cosine theta plus the power which is dissipated in the copper as well as the power which is dissipated in the core, which is represented by this is RC, multiply 100%, right? This particular expression of efficiency, this is only valid, this is valid for full load or rated current, which means that in here we have this copper loss which is dependent on this current. Because this PC is fixed, this is a standard expression for the output power. So for this P copper, for example, we have the P copper is equal to I square in full load into the R equivalent, right? So suppose that I have a load which is half of the full load current, right? I have a load which is half of the full load current. Then the P copper losses at half load is equal to I full load divided by 2 times square into R equivalent. So which means that 1/4 of the power loss remains when we are operating at half of the rated current, right. So you can see here that at full load the copper losses are maximum. If we reduce it to half load, we get only 25% of the copper losses. What I mean to say here is that I want to incorporate this this particular thing into this equation for this efficiency. Right now it is not here. It is not here, right? Why it is not here? Because this equation is only valid for the full load current. If I want to incorporate this particular thing, that I can calculate the losses on every instant of a loading condition, if it is full load, half load, or we have applied 1/3 of the rated load, then I can say that this P copper loss is equal to X square into P copper loss full load, where this X is equal to what? It is the ratio of the current divided by the ratio of the secondary current to the full load current. So if I have half of the rated current, then that is equal to 0.5 I to full load divided by I to full load, then this X become equal to 0.5. And if I apply this to 0.5 here, so this becomes equal to P copper full load, that is equal to 1/4 of the copper losses at full load, and this is what we have explained here, right here, right. This is what we have explained here. So if I want to incorporate that into the efficiency expression, then I have this efficiency equals to VSIS cosine theta divided by VSIS cosine theta plus P core losses plus X square PCU full load, right? X square PCU full load. So this X square defines the per unit loading, right? It is the per unit loading. So let me write this as this X square is the per unit loading, or the loading of a transformer. How much this transformer is actually carrying the current. So if we have 1/3 of the rated current flowing from the secondary side, then this X is equal to 0.33. So we have to take it to this 0.33 square, and that's thereafter we can get the value of the efficiency. And of course this efficiency is into 100%, right. So this is, I think, now clear. Let us move ahead a little bit. We also need to establish that at what point the efficiency is the maximum for a given transformer. So we have seen that the efficiency of a given transformer is dependent not only on the power factor but also on the amount of current flowing, because that current is determining the copper losses in a given transformer. So to establish the maximum efficiency of a transformer, we start with this particular expression. N is equal to this VSIS cosine theta divided by VSIS cosine theta plus P copper loss plus P core loss, right? Where this copper loss, I can rewrite it as IS square into R equivalent, right? Let us keep it to the full load value, and thereafter we can actually see how this full load value is actually varied with respect to the amount of current here, equivalent. Now this can be cancelled out with this one. So this PC equals to IS square into R equivalent. What is this one? This is the core loss. And what is this one? This is equal to the copper loss, right? So we have seen that we can get the maximum efficiency of a transformer if we set the current through a transformer such that the core loss becomes equal to the copper loss, right? So when we have this core loss equal to the power loss, then the maximum efficiency is achieved, right? Then the maximum efficiency is achieved. Also, this maximum efficiency, if this is the 100%, we say this is the efficiency in percentage. Here we have this 98, then we have this 96, then we have this 94, this is 92, this is 90, and this is a long value. And also we have this one as the percentage loading 0.6, 0.8 and 1, right. This is the current I, where this is X, that is equal to IS divided by IS at full load. So if we say that this X axis we have the loading available, loading factor available, that at here we have 20% of the full load current. So this is 20% of the full load current, and here we have 100% of the full load current, 100% of the rated current, right. Here we have the 20% of the, let me write it in terms of the rated current, which is also the full load current, right. So 20% of the rated, which is the full load current. So here we have this 100% of the full load current. Then we have some sort of a waveform slab, something like this one, where this one is for unity power factor, that is equal to 1. This is for power factor equals to 0.8, and this one is for power factor equals to 0.6. So now you can see here that this transformer efficiency is maximum when we have a unity power factor, and in that unity power factor we have one particular instant where we have the maximum efficiency, somewhere here. It could be somewhere here, because this diagram is not up to the scale. It is just an idea that gives you that in order to have a maximum efficiency, the current should be such that the copper loss should be equal to the core loss. And when this happens, that particular point gives you the maximum efficiency of a given transformer, right. So we'll stop here for this particular lecture. So till the next lecture, take care and Allah Hafiz.